Have you ever stood in a giant skyscraper and wondered how the air stays fresh? Or how a hospital keeps its air sterile for patients? Well, today, we're going to pull back the curtain on the unsung hero of our modern buildings, the Air Handling Unit, or as we call it, the AHU. Think about it for a second. What are the lungs of a modern building? And that's not just some poetic question. The answer is a critical piece of engineering that is absolutely vital to our comfort and our health. We're talking about the AHU. It is literally the respiratory system for our entire built environment. So what is an HU, really? Well, the textbook definition says it's the powerhouse of the whole HVAC system. Its job is to heat, cool, filter, and move every single cubic foot of air you breathe when you're indoors. It might look like just a big metal box from the outside, but inside, there is a whole symphony of engineering going on. So in this explainer, we're going on a deep dive. First, we'll cover the basics. Then, we're going to tear one of these down to see what's inside, piece by piece. We'll look at the big design choices, learn how engineers pick the right unit for the job, and even cover some crucial rules for installation. All right, let's get into it. Okay, it's time to pop the hood on this thing. We are going inside the air handler for a full component-by-component tour. You're about to see what really makes these incredible machines tick. At its core, an AHU is all about process. You have air coming in one end, it goes through a whole series of treatments, and then it comes out the other side, perfectly conditioned for whatever space it's headed to. So let's break down each step of that journey. First up, you've got the fan. Look, if the AHU is the lungs, then the fan is the heart. It's the muscle that pumps air through the whole system, pushing it through the filters, pulling it across the coils, and sending it out into this huge network of ducts to reach every single corner of the building. And we're not talking about just any old fan you'd buy at the hardware store. Engineers get really specific, choosing types like centrifugal or plug fans. Their capacity is measured in cubic feet per minute, or CFM. Now here's a key takeaway for any of you future engineers out there. For maximum efficiency, modern AHUs almost always use something called a variable speed drive, a VSD. This lets you control the airflow with incredible precision, which saves a massive amount of energy. Okay, after the fan, the air hits the coils. This is where the real temperature magic happens. You've got either hot water, chilled water, or some kind of refrigerant flowing through these super intricate coils, and their job is to either add heat to the air or pull heat out of it to get it to that perfect temperature. Now, the design of these coils is all about one thing: maximizing heat transfer. That's why they have all those fins. It's to increase the surface area. And the choice of material you see here, copper, aluminum, steel, that's a critical balancing act between performance, how long it'll last, and of course, cost. And its power? We measure that in BTUs per hour, the fundamental unit of heat energy. Now, before that perfectly tempered air can actually reach you, it has to be clean. And that is where the filters come in. You can think of them as the silent guardians of our indoor air quality, trapping everything from regular dust and pollen to much more harmful contaminants. And let's be honest, in today's world, this component is more critical than it has ever been. So, the key spec here is the MERV rating. That stands for Minimum Efficiency Reporting Value. Basically, the higher the MERV number, the smaller the particles it can trap. But, and this is where it gets really interesting for engineers, there's a trade-off. A higher MERV filter is much denser, which creates more resistance to airflow. We call that pressure drop, and that means the fan has to work a lot harder and use more energy. The real art of engineering here is finding that perfect balance between perfectly clean air and energy efficiency. But wait. Before any of that stuff happens, a really important decision is made right at the beginning, in what's called the mixing chamber. The system has to decide, do we reuse the air that we've already cooled or heated inside the building, or do we bring in fresh air from the outside? This is where that blend happens, and it's a huge choice that impacts both energy use and air quality. And that one decision brings us to a fundamental fork in the road for AHU design. We're talking about the two core philosophies, recirculating air versus using 100% fresh air. This is a critical distinction that every engineer has to master, because it basically dictates the whole purpose and application of the unit. So at a high level, the trade-off is pretty clear. Recirculation units, like the name says, they reuse the air that's already in the building, and they just mix in a little bit of fresh outside air. This is way more energy efficient, right? Because you're reconditioning air that's already close to the right temperature. On the other hand, you have 100% makeup air units, which are constantly bringing in fresh air from outside. The air quality is amazing, but it comes at a much higher energy cost. And here is where the rubber meets the road in the real world. For most buildings, think offices, schools, your home, a recirculation unit with a decent MERV 8 or higher filter is the perfect sweet spot between efficiency and health. But in critical environments like a hospital operating room, a science lab, or a clean room, you can't compromise. You absolutely need a 100% outside air system, and you'll pair it with super high efficiency MERV 13 plus filters to guarantee purity. No exceptions. Okay, so you get the components, you understand the two main designs. So how does an engineer actually choose the right unit for a specific building? Well, that all comes down to a few key selection parameters. It's really a big balancing act. It all starts with the load calculation. That's figuring out how much heating and cooling in BTUs the building actually needs. That number then dictates the airflow rate you'll need in CFM. From there, you layer on the filtration requirements. You calculate the system's resistance, or what we call static pressure. And then you have to weigh all of that against your targets for energy use and how much noise is acceptable. It's a complex puzzle with a lot of moving pieces. Now, here's a classic rule of thumb that every single HVAC student and engineer needs to have in their back pocket. For standard comfort cooling, you're looking at about 400 CFM of airflow per ton of cooling. And remember, 1 ton of cooling is just a shorthand for 12,000 BTUs per hour. This is an incredibly useful shortcut for quick, back-of-the-napkin calculations early on in a project. But where does that rule of thumb even come from? It's not magic. It's all based on this fundamental formula right here. The required airflow, your CFM, is equal to the sensible heat load, that's the Q, divided by a constant 1.08 times delta T. And delta T is just the temperature difference between the air in the room and the air coming out of the vents. This equation, this is the physics that underpins the entire practice. So we've designed it, we've selected it, now we have to actually install this massive piece of equipment. And let me tell you, planning the stage properly is absolutely critical for the success of the whole project. Here are 5 non-negotiable rules for space planning. 1. Double and triple check your dimensions. 2. You absolutely must leave at least 36 inches of clearance all around it for maintenance. 3. Make sure you have enough headroom for all the ductwork. 4. Plan your access route. How are you even going to get the machine into the building? And 5, make sure your foundation can handle the weight. I promise you, get any one of these wrong and you are in for a world of pain. And you always have to remember, the AHU doesn't work in a vacuum. The design of the ductwork is just as important as the unit itself. By optimizing your ducts, you reduce that static pressure we talked about earlier, which lets the fan run more efficiently, and that saves energy and money over the entire life of the building. And all this brings us to a final, really critical question, especially for the next generation of engineers. As we design the buildings of the future, what's our top priority? Is it maximizing energy efficiency to help tackle climate change, or is it guaranteeing pristine indoor air quality for our health and well-being? The answer isn't simple, and how you choose to solve that puzzle will define the future of climate control.